Yep, today I'm going to be talking about a polynomial time classical simulation of noisy circuits with naturally fault-tolerant gate sets. I'm excited to be here. Thanks for having me. This is work that we've posted on the archive recently with John Nelson, Dominic Hengleiter, and Michael Billins over at the University of Maryland. Dominic's actually moved to Simons recently. The way this is going to go is I'm going to try to motivate the problem that I'm talking about, give you some background on the details necessary, and then I'm going to state the result. This is a classical simulation algorithm. So first I'm going to try to give you some intuition for how the algorithm works. And then in order to prove that it actually works, we have to develop some new analysis tools, and I'm going to try to give you some intuition for that too. And then I'm going to talk about future work. So the motivation for this studying classical simulation algorithm is looking at quantum advantage in sampling. So this is a very vague statement, but it's intentionally vague because basically we know that quantum circuits can give some advantage in sampling. It could be for the task as cool as factoring, or it could be something simple like random quantum circuits. These are just examples of tasks for which the output distribution of a quantum circuit is hard to approximately sample from. Now, when you implement them, they're noisy, and there's a lot of things that may go wrong. But for that, there's actually this nice result, which is also old, that noisy quantum circuits can be made fault tolerant given either fresh ancilla or reset gates, and intermediate measurement and classical feed forward. So you kind of have these two results that tell you that you can demonstrate quantum advantage with quantum circuit, and then it can be made robust. But what's the problem is that near-term hardware can't do both of these things simultaneously. It doesn't have the operations necessary for both. So, and this is sort of what we called in this era, and but that can be made more formal. The main question that I'm going to be asking in this talk and trying to get at is what restrictions can we place on a quantum circuit to rule out the possibility of scalable quantum advantage in the presence of noise? So, as I mentioned earlier, you need fresh ancilla, for example, or you need to do classical intermediate measurement and classical feed forward. If you remove this and maybe you make other restrictions, can you say for certain that the circuit class cannot be made fault tolerant, cannot demonstrate quantum advantage? So I think this is interesting for two reasons. One, it lets you assess current experiments. For example, if it's not true, then maybe you could classically spoof quantum advantage demonstrations. And it also helps you guide future experiments. So if you can narrow down specific restrictions that rule out quantum advantage, then it's sort of getting at the idea of what are the implementation details that make a quantum task easy or hard. And maybe you can search for hardness on the other side. So how do you rigorously rule out this scalable quantum advantage? You provide a polynomial time classical simulation algorithm. So,
and that's basically actually also the only way doing it, right? I mean, given that we have no separation known between PQP and P, right? Yeah. All we can ever do is that.
Yep, yeah, that's true.
Yeah, okay.
So,
sorry, before you meant, or mid-circuit measurement or fresh auxiliary, right?
Yes,
no?
Yeah.
Okay.
Is that what are you talking about here?
Yes. I mean, you can also remove intermediate measurements and have just fresh auxiliary, right? I mean.
Yes. So it's either fresh ancilla.
Okay, great.
Can I ask one more question on this?
Sure.
So you say that, at least you imply that for quantum advantage, you need some sort of fault-tolerant quantum computation. Do we know whether we can have quantum advantage with noise or some some tolerable amount of noise?
So I think it's known that if you scale the noise with this down with the system size, then we can demonstrate this. But I think for a constant amount of noise, it's not yet shown.
I see.
I'm going to be talking about that in a sec.
Cool.
So I'm going to be looking in this work at two types of circuits, and you'll see this is also sort of just because it helps the proof work, but it's also interesting just to look at these circuits and understand what happens when you restrict the gate sets. The first is the IQP circuit. This has state prep and measurement in the Hadamard basis. and circuits constructed from diagonal gates. So these were recently implemented experimentally by this collaboration out of Harvard, QR, and UMD. So they're sort of interesting experimentally as well. Another sort of related circuit you can think of is a Clifford magic circuit. We're calling it a Clifford magic circuit, but it's a similar thing has been talked about in other work, also called Clifford magic circuits. Basically, this is state prep and measurement in an arbitrary, and you choose a magic basis probably. And circuit is now constructed from Clifford gates. The original Clifford magic circuit didn't involve magic on both sides. It was just magic at the input. But we're sort of generalizing it and calling this the Clifford magic circuit. And you can see it's sort of similar to the IQP circuit. Here the resource is magic, there the resource is sort of coherence.
But what about to I mean, there's no mid-circuit measurements, right? To be sure.
Yes, no mid-circuit measurement.
Because otherwise, then the magic would be vastly different. I mean, well, basically, there's nothing Cliffordness remaining if you allow for magic measurements along the way. Never mind. Okay.
So, sorry.
Sorry, but maybe now another meta point, which is you're the boss of your talk, right? If we are known to ask many questions and they are very friendly and by no means anyway offensive and so on ever, but there might be many. So if you think you're derailed or there's too many, just say, I'm the boss of my talk, shut up, please. Okay.
Yeah.
So far, I think
okay. No, that's good. I told you.
Okay, I will ask the question if I can, and you are the boss. And okay, you say it's fundamental that you have magic input state and magic gates at the end. You cannot have in the middle, or you can assume that without some loss of generality in some cases. I mean, can you say about this? I mean, you are making a strong assumption or not there?
No, that's you cannot do magic in the middle. You can only introduce the magic at the end or at the beginning. And,
okay.
Yeah.
Because I mean there are these stabilizer extent algorithm that says it's sufficient to do a Clifford with magics, but you need some forward mid-circuit measurement, right? To inject magic.
Yeah.
Okay.
So they deal with intermediate magic by injecting magic state. And one thing that maybe is different from those is that here I'm introducing magic on all n qubits. So this would, if you had tried to use one of those simulators, it probably wouldn't work because you're introducing n qubits, which are all magic. So your stabilizer, whatever technique you use, it would have a cost of 2 to the power n.
Okay, great. Thank you. And just another meta thing, can you maybe reduce from Zoom the column of the speakers because we cannot see the right part of your slides? If you can reduce to...
That's right, because Zoom has the tendency to not show what you have on the screen, but block your screen.
Okay, yeah.
Okay, wonderful. That's great.
Now, maybe you don't see us, but you could also do just one window or instead of a column. I don't know, as you prefer.
Okay.
Can I also ask something before going on? Sorry, other questions. I'm curious. So these drawings have this brickwork like gates build up. I'm curious. Should I think of them as a lot of 2-qubit gates? Or should I think of them as arbitrary? Like is there some scaling of the depth or like the width of these Cliffords?
So the brickwork is just to make it easier to draw. So
okay, sure. Thanks.
But all of the gates are 2-loc, like they act on 2 qubits. They just may not be on like a geometric, like this is a 1D system. It may not be like that.
Amazing.
So why am I interested in these in circuit classes? One is they can demonstrate provable quantum advantage. That's with the star, but up to complexity theoretic assumptions, they're hard to approximately sample from. The thing that kind of makes these restricted gate sets interesting is that they're non-universal gate sets. So, and we say they're like naturally fault tolerant in a sense. The idea is that this might be implementable on near-term hardware. For example, the fact that an IQP circuit has restricted gate sets is what made this slightly implementable in the Harvard Q-era UMD collaboration. So, I mean, the idea is like, when you restrict the gate sets to something that still gives you quantum advantage, what happens? And really, the reason why we were actually thinking about Clifford magic circuits is we were trying to make progress towards general quantum circuits. For example, certain properties of random circuits resemble random Clifford circuits, like second, third moment quantities. So we were actually trying to make progress towards random quantum circuits, and we chose Clifford magic circuits as like an example, a step along the way. So the task that I'm going to be trying to do is to maybe formally define it, is to approximately sample from the output distribution of a noisy quantum circuit with no fresh ancilla or intermediate measurements. And the way we've modeled the noise is depolarizing noise of a constant strength after every on every qubit in every layer. So one interesting thing is that existing work in this model, there is a large body of existing work, but a lot of it actually requires the output distribution of the circuit to anti-concentrate. And this is because anti-concentration comes up in proofs of easiness and hardness, so it makes sense. But what this means is that it actually can only be an average case statement. So for example, it works for random circuits, and so it can't exclude a worst case circuit. And the reason why I see is more of like a symptom of the proof techniques. Proof techniques require anti-concentration and require this sort of randomizing over the gates so you can get some statement about the way noise acts. And so you can't exclude the worst case circuit. And then
can I ask another question on this? Sorry, but well, I mean, obviously you must know that Dominic was also here for many years here in the team, so we have a very strong joint history. And we've been wondering about the notion, the role of anti-concentration. And of course, anti-concentration plays an important role in the proof techniques, and we have like Stockmyer machinery to like uplift multiplicative errors to additive errors and all that. Yeah. That said, it's not clear to what extent we really ultimately need anti-concentration to have an average case hardness result. Right? So in principle, there could be other proof techniques that show similar results without anti-concentration, right? Can you confirm that?
I believe so. But I don't know how to prove it. But for example, one thing you could do is you could take an anti-concentrated circuit and code it in a circuit that doesn't anti-concentrate. Now the circuit may not be like the output distribution of this new circuit would be hard to sample from and provably, but now it itself doesn't anti-concentrate, so it's not simulatable by a lot of existing work.
Okay, fair enough. Okay, good.
So yeah, so we're trying to look at worst case circuits, right? Because we're trying to figure out a way to rule out quantum advantage. So now it's sort of a novel thing we're kind of exploring. So I'm going to state our result with this theorem, and I'll try to condense it into a simpler statement a little later. Suppose C is a noisy quantum circuit of depth D, which is either an IQP circuit, a Clifford magic circuit on an O of 1D lattice, an IQP circuit with C0 gates on an O of 1D lattice. So like this can be a 2D, 3D, 4D, as long as it's O of 1. There exists a constant depth threshold, DC, and such that when D is greater than DC, there is a polynomial-time classical algorithm which approximately samples from the output distribution of C. So this is basically our main result. Here, if you remember, gamma is the noise strength. We're fixing the noise strength to be a constant. And this is saying regardless of whatever that constant is, once you choose it, it sets a depth threshold. The case for an IQP circuit is actually an earlier work also out of some people out of Maryland, me, James Watson, and Yikai Liu. And this is basically improving upon that with new techniques that let you think about Clifford circuits and IQP circuits with C0 gates. So,
sorry, just a very kind of naive question to clarify. If the depth is below this threshold, this is all kind of constant depth circuits to you, so anyway you expect to be able to simulate that. Is that the argument? So like
not completely. So I think so. Like that's what I think might be morally true, but it's actually not that hard. It's not that easy to show sampleability of the constant depth circuit.
Okay. What prevents me from what prevents me from taking a circuit of a certain depth? If my depth is too short, what prevents me from taking a depth that's too short and then just padding it with identity gates to formally be in the setting of your theorem?
Because you would need the noise. So in the setup we have, there's noise after each layer. So yeah, if you did add as many identity gates and develop that noise, it'd work.
Yeah, got it. Okay, thanks.
Sorry, can I ask another question? But then I will just shut up for a while. So as you might know, we've shown here that Antonis sitting next to me. We thought quite a bit about like new simulation algorithms for non-unital noise and what you could say about way you have effective log depth and so on. But we've been struggling of generalizing our theorems to non-unital noise. So for now, when you say noisy, you mean depolarizing noise. You just shrink the block sphere. Is that correct?
Yes, I mean depolarizing noise.
Very good. I missed that.
Pauli channels goes similar, or it's strictly depolarizing noise here?
So in the case of IQP circuits, you can also do dephasing noise, or basically any poly noise channel with a dephasing component. But for Clifford magic circuits, I think we need a depolarizing noise. Well, so it can be any poly noise channel as long as you can like kind of extract out a depolarizing component.
Okay.
So like you could have it biased towards Z, but that's as long as there's still a small component of X and Y, that will cause the simulation algorithm to work.
Okay, thank you. And yes, and also your work covers previously after log n, it was known that with depolarizing noise, I mean, you can just sample from the uniform distribution, but
yes,
from your constant threshold of depth until log n, it was still open. The question of quantum advantage. Yeah.
Yes.
Okay.
So I have a graphic that will show that.
Okay. Yeah. So yeah, there was another question, I think.
No, it's me.
Okay. Thank you.
So yeah. Put simply, it's a polynomial-time classical simulation algorithm for sampling from any noisy circuit in the IQP or CM star. So that's what I'm calling Clifford magic, which is on this O of 1D lattice, beyond an O of 1 depth. So to place it with the existing result, as Antonio mentioned, we already know that once you go past log n depth, your circuit is simulable because the output is close to uniform. This is because of you're using a depolarizing channel that just increases your entropy. And then it's also known for an example of something that is true for this restricted circuit class, IQP circuits are simulatable in the average case. So this is true if you have this anti-concentration property, then Bremner, Montanaro, Shepard have shown a simulation algorithm. When they proposed it, it was actually a log n depth algorithm. What our results are showing is that actually you have an onset of classical simulatability within these circuit classes at omega 1 depth.
And sorry, can I ask a question? And are your new results for any circuit or in average case as well?
It's for any circuit, so that's why we were able to rule out the worst case circuit.
I see. So it's really much better, even, or at least better, even in the region where they overlap. I see.
Yeah. Well, so one thing is this Bremner, Montanaro, Shepard result. It was later shown, so it works for any IQP circuit that is anti-concentrated. And then later it was shown that you can actually construct this clever IQP circuit that is anti-concentrated at constant depth. So like, and that's why there's a star there, basically. The idea is that whatever depth you anti-concentrate at, this simulation algorithm would give you as a result.
I see. Yeah, thanks.
So just to sort of get at like maybe the intuitive, just like a more intuitive way to look at this is you might think like the experimentalist intuition is that if I have a 1% probability of error per time step, of course my circuit should be useless after 100 time steps or something like that, right? And the reason why this isn't true, like formally, is that this is only true for a single qubit in isolation. And the whole point of this fault tolerance in like some of these old results for Aronoff, for example, is that fault tolerance is actually possible if you encode this redundancy, increase your system size, and you're able to go past this, like what you might intuitively think is that you can only go up to 100 time steps. So basically there's this possibility of noise robust quantum advantage before you get to omega log n depth. And I think someone asked about this. This is sort of open. There is the possibility that you can demonstrate sampling advantage in this regime. We haven't constructed the circuit for that yet, but it's possible. It would be very cool if you did. what our results are showing is that whatever circuit you tried to construct, if you restricted yourself to be in the CM star or the IQP circuit class, they would be simulatable at this particular depth. So maybe some of the things you could try is to go outside of this framework. And that's sort of the message of our work, is that if you want to demonstrate noise robust quantum advantage in this regime, by restricting these gate sets and taking away fresh ancilla and intermediate measurement, you're making it so that you're not able to take advantage of the redundancy anymore. And you lose your quantum advantage at constant depth, which is the intuitive thing you might have thought was true.
Sorry, can you please repeat this last sentence that you said? I mean, if I understand correctly, you said that you have to restrict, otherwise, you know that you cannot have a worst case algorithm until log n. I mean, what is the statement that you said?
So yes, if you restrict to Clifford magic or IQP circuits, then now you know that when you go above a constant depth, you are classically simulatable. What this means is it returns you back to this experimentalist intuition that if I have a 1% probability of error, my circuit is useless after 100 time steps, regardless of my system size. So earlier you would have thought that you can increase your system size to get some redundancy that lets you go past this threshold, and that's what Aronov talks about. This is showing that when you go to CM star or IQP, you're not able to increase your system size and do that, increase your depth in any way.
I see. So the Aronov paper 96 showed that log n there is no, if the BQP is different from BPP, there is no classical algorithm to simulate noisy circuits with depolarizing noise, even if you don't have fresh auxiliary and measurement. I mean, if you relax this assumption of IQP, then Aronov from what Aronov wrote in that paper follows like there is no classical algorithm. That's
kind of. She basically shows that it's possible to encode all of Q and C1 computation in a noise robust circuit up to log n depth.
Yeah. Okay.
So if you believe
without fresh auxiliary, right? And
without fresh auxiliary, yeah.
But in a different, like maybe mathematically equivalent, but psychologically inequivalent way, citing Feynman again. This kind of different, like omega-1, omega log n behavior is a bit similar to the results of like Raoul and Daniel Silch-Franca on showing that if you have polylog depth of a circuit, you are kind of close in the trace distance to the maximally mixed state at the output. In log depth, you are not close to uniform, not to the maximally mixed state, but you are in the Gibbs sample rebord. This separation is kind of mapped out here in a way, right?
Exactly. In fact, that was one of the papers I read very early in my PhD that sort of inspired this line of thinking. So that's exactly what I've been thinking about.
Okay. I mean, yeah, good. Yeah. Thank you. Very good. Then I'm on the right track.
Yeah. So another result we have, which is maybe not as impressive, but it's sort of analytically kind of interesting, is that if C is a noisy quantum circuit, which is Clifford magic or IQP, but now you've relaxed this O of 1D lattice requirement, so now it can have any locality. There is a depth threshold, which is gamma to the -1 times log n, such that when D is greater than DC, there's a polynomial-time classical algorithm. This is not that great, but if you notice, it's still before the output distribution is completely random, which formally requires you to go beyond log n depth. So you can kind of compare this to, for example, there's this recent work by Aronov et al., which talks about random quantum circuits, and that exactly works in this depth threshold of gamma minus of log n depth. And basically what we're saying is that maybe you're able to relax this average case and anti-concentration requirement when you look at worst case Clifford or worst case IQP circuits with C-naughts. But this is just another thing that we have in our paper, and I may mention it later.
Sorry, the difference with theorem 1 is the geometrical connectivity, right? Or what?
Yes. Yeah.
Okay.
Yeah.
Okay.
So I'll try to give you some intuition for the algorithm. How much time do I have?
I would say half an hour,
Okay.
more or less.
Yeah, but be chill. I mean, 0.
Yeah. So the algorithm goes in 3 steps. The first step, these are just the titles of the step. I'm going to explain them a little more in a sec. First, we sample Pauli projection channels. Then we induce percolation in the circuit connectivity. Finally, we'll see a phase transition for classical simulatability. So the first step is sampling Pauli projection channels. What are these? These are basically, we've defined them as a channel where you apply the identity with half probability, and otherwise you apply a given Pauli operator. So this is a Pauli projection channel. In a sense, you're sort of projecting along a certain basis. Now, the idea is single qubit depolarizing channels can be modeled by a stochastic process, and with probability 1 minus gamma, you do nothing. With probability gamma, you replace a qubit with maximally mixed state. You have these depolarizing channels throughout your circuit. Now, what we're going to do here is, instead of thinking of the depolarizing channel as this channel, this replacing the qubit with the maximally mixed state operation, you can think of this as applying a projection in the x, y, and z basis simultaneously. So with probability 1 minus gamma, you do nothing. With probability gamma, you now project along x, y, and z. So now this gives you sort of maybe an idea of how you could simulate this. Is for all of these noise channels in your circuit, you flip a coin. With 1 minus gamma, you do nothing. With gamma, you sample all the projection channels. Now, once you do that, this is sort of shown in the diagram here, then since this is a Clifford circuit, you can propagate these channels to the beginning, where they stay Pauli projection channels, but now they become very non-local, right? This single qubit X projector may turn into a very complicated high weight Pauli projection channel. But you have many of them, and the longer depth you go, the more channels you're going to have. So you combine them all, and we actually show there's like a simple way you can check that if there's enough of these Pauli projection channels building up together, some of these qubits are going to be so faulty, have so much projection happening on them, that they are actually effectively replaced with the maximally mixed state by the error channels. And we can show this formula. And so the main idea behind this is that instead of sampling the evolution of a channel as a CPTP map, or instead of sampling errors like X errors, Y errors, or Z errors, if you sample this projection channel and you actually increase mixedness in a way that's easier to analyze, you're able to say that many of my input qubits become the maximally mixed state, and they are actually maximally mixed state.
Can I just ask Joel? I think I misunderstood then. The depolarization channel is a local depolarization channel on each qubit?
Yes.
Okay. So when the constant gamma that you put in is a constant gamma for, as I put in more qubits, I will have a larger global depolarization channel as time goes by. With more qubits, I will have a stronger error in general.
Yeah, you'll have a stronger error, but it's not exactly a global depolarizing channel. Right?
No, completely correct. I said wrong there. Thanks.
Yeah.
And sorry, is it approximately sampling, right? Or from the output distribution, or is
So I'll get to that in a second. Yes, the target is approximately sampling.
okay.
So here we haven't gotten to the output distribution yet. We're just sort of looking at the noise in our circuit and dealing with it in a way that avoids having to think about like a MPO or something like that. That you're sort of just using the noise to remove some of the entanglement. So I guess that's the next step, which is that now let's sort of look at my circuit a little bit more abstractly. Every vertex I'm going to represent, every qubit I'm going to represent by a vertex. I'm going to say 2 qubits have an edge between them if they have intersecting light cones. So I sort of showed a light cone in the previous slide. That's this triangle coming out in the gray. Hopefully you guys may be familiar with this concept, but the idea is that 2 qubits can only be entangled with each other if their light cones intersect. If they don't, then you can't develop any correlation between them. If you trace out one of the qubits, the state of the other qubit is not affected. So this graph kind of carries information about the entanglement structure of your circuit. And in general, it's going to be a pretty dense graph because a lot of them are going to share neighbors. Now, the idea is that once you've sampled your noise in this way, and you've replaced some of your input qubits with maximally mixed states, well, now that they've replaced with maximally mixed states, the gates that act on them later on in the circuit kind of act trivially because they're acting on maximally mixed states. So they aren't developed, you can't introduce entanglement between two maximally mixed states. And effectively in your graph, you're going to see edges being removed from your graph. That's one way you can think about this. And the idea is, if you have enough buildup of noise, you're going to remove enough edges that your graph splits into small little subcomponents. And once this happens, all of the entanglement is within each subcomponent, and the resulting components can be simulated independently. Does this make sense?
It's a really cool way of doing it, Joel. Can I just ask, you need both parties to be maximally mixed in order to remove them at the level of percolation, right?
Yes, yeah. So I'm sort of maybe hand waving my way through that, but yes, you need both of these qubits to be maximally mixed. In the IQP case, you actually don't need both. And it's actually a little bit more complicated than that in the analysis. It's more that you kind of need a giant square to become maximally mixed. And then you can say something about the square within it, if I'm thinking of a 2D lattice, for example.
I see. Like, I mean, many years ago, together with Dominic, actually, we started looking at percolation in this context, but more in the converse approach. It was like more like, can you have parts connected? Not so much, can you not have them connected? You're like more on the, can you not have them connected side? But in the end, you make an edge percolation problem out of this, right? I mean, you remove edges when they are too mixed, and then you want to see other kind of clusters, and then if the clusters are not large enough, then you kind of keep them separate and can simulate them efficiently classically. Is that right?
Yes, yes.
Okay. Interesting. Yeah, that reminds me also, we recently, you might have seen this, we had this results like with Amanda and others, this result on decoders for LDPC codes, which were practical and so on, like a completely different realm, but in the end, the techniques were kind of similar in that we did like belief propagation and ordered statistics decoding, but at the end, to make it efficient, it was important that we had clusters that didn't grow too much and that they could be treated separately in a decoding problem. But it's not so dissimilar that we could do the decoding for them being separate and you would do the simulation for them being separate.
Oh, I see. Yeah, I should look into that. That's a really cool connection.
Yeah, I can send it to you.
Can I just ask one thing I didn't catch 2 slides ago? I thought you were going to explain that with the interaction graph, but it seems like it's actually different. So your point C is you replace very faulty input qubits with these maximally mixed states. How do you decide which qubits to replace? I didn't catch that.
Yeah, so I guess I didn't say that explicitly. What you do is you combine all of these channels at the beginning. Sorry, these projection channels at the beginning. There's a simple text that I'm not mentioning here, but each of these is a poly error, and essentially what you're going to check is just check whether it generates a single qubit X and a single qubit Z. If somehow you can combine these projection channels in a way that they sum up to a single qubit X, and that's the condition I check. And if that condition is true, then I know I can replace that qubit with the maximum mixed state.
I see.
Yeah.
Sorry, Joel, I have another question about this slide. Okay, so from step A to step B is just exact analytical rewriting, right? You just commute the polarizing noise that is Pauli channel through the Clifford circuit at the beginning, and you can find if in Polynomial-Time another description. And then you basically observe that this initial layer, I mean, you can just sample each qubit with some probability efficiently, and in some qubits you will have identity. And these that you have identity are you just put this thunder and this maximum state, and you have two locations that you can do your light cone arguments. And so every step here is not approximate, is exactly simulating the circuit exactly, right?
Yes. I've made no approximations yet.
Fantastic. Okay, thank you.
So now, yes, there's going to be a phase transition. And how do I prove to you that this phase transition happens at constant depth? So from graph percolation, we know that for any graph, if delta is the maximum degree, Q is the probability a vertex survives. Then when Q times delta is less than 1, its connected components are of size O log n with high probability. I have this small graphic that I show just to show that it's actually a very intuitive statement and then not really that fancy math. If you have like a 5-degree graph and you have a probability of your error being 1 over 5, well, the first step, you're only going to have one neighbor. And then your second step, it's very unlikely to have another neighbor. So you can think of this like as a chain that ends pretty quickly. So it's unlikely that you're going to get connected component of size O log n. This is just to show, like, intuitively, this is a pretty simple statement. But in our setting, we're actually able to map it very precisely, which is that in an O of 1D lattice, the light cones only expand polynomially. So if you have a qubit, it's in the first layer, if you have a circuit of depth D, if it's on a 2D lattice, then it can only interact with D squared, order D squared many qubits in the square around it. So you can actually say, if it's like capital D dimensional, then it's D to the power capital D is sort of the light cone around a single qubit. So the light cone only goes polynomially. But at the same time, since we're increasing the depth and moving the noise to the beginning, there's a certain probability a qubit survives the first channel, and then the probability it survives the first and the second builds up, and the first and the second and the third, it builds up, and actually this buildup is exponential. So you have that each qubit survives, doesn't have an error with exponentially decaying probability. So just kind of applying this percolation result, phase transition will occur when poly D time D minus gamma D is less than 1. And this happens after constant depth. And this is where you get this phase transition at constant depth. And after that, each subcircuit is of log n size, and it's simulatable in polynomial time.
Interesting.
So
That's actually interesting. But may say that it's really very similar to the argument for decoding. Because I mean, there's also a decoding transition if you want. A decoding phase transition for very similar reasons.
I see. Yeah. But yeah, so like, yeah, I just want to kind of highlight this main equation here, because this is kind of getting at the heart of what is happening here, which is that there's this fight between entanglement and noise. And what the precise statement is saying is that your entanglement cannot grow as fast as your noise is. So as you increase your depth, you're not able to combat the noise, and eventually you reach classical simulatability. So so this is sort of, so sometimes you may, when you hear this word, you may think, oh, I've fixed the depth, and so I've fixed the noise strength and I found a phase transition in depth. This is kind of similar to fixing the depth and finding a phase transition in the noise strength. But actually, it's a little bit more subtle, because what I've actually shown is that you can't increase, if you keep increasing the depth, smaller and smaller noise strength is enough to make you classically simulatable. It's that, like, it sort of goes against the intuition, which is that depth should let you build up entanglement and avoid noise. Actually, that's not true. Just pathologically, you can't avoid the noise.
Sorry, like if you have for a convex combination between maxi and mixed and something that as like depolarizing, but it's not depolarizing, it's Pauli channel. I mean, where these arguments breaks? You said that the ear works for depolarizing, and I mean, but this kind of percolation argument seems to.
But you need to like remove edges, right? And that must be presumably also that can only be true for very simple noise, because we have to have a logic where you just remove parts and not treat the full quantity.
He relied pretty strongly on the fact that you could write this channel as a Pauli projection, a sequence of these 3 Pauli projections. Right?
I think so too, but maybe we should also let the speaker answer the question.
No, but that's
we have so many opinions about this. This is terrible. Sorry about this.
Yeah, that's correct. It's because, yeah, I use this poly projection. So it would work for any poly noise channel where I can extract out a depolarizing component. But so you can have X, Y, and Z of different probabilities, but as long as each of them is at a constant probability, it'll work.
Okay, so composition between depolarizing and something else also works. Okay.
So
I have small questions though. Sorry, is it possible still or?
sorry.
One small question. So I mean, assuming I would have a noise channel and like the dephasing channel that actually has more than one fixed point, does that actually like, is there an assumption in there that that is necessary, or would that still go through?
Sorry, could you say that again?
Like if I have more than one fixed point, like I have a noise channel that has more than one fixed point, like the dipole channel has only one fixed point.
Yeah.
Like dephasing would have two. Would that change a bit? Like I mean, in terms of like replacing faulty qubits with something, because I wouldn't know, right? And because on a block sphere, I wouldn't necessarily be close to the maximum mix that it could be.
Yeah, I think, yeah, if it has multiple fixed points, then yeah, that's maybe a good way to differentiate it. Yeah, that's it won't work. And I guess you can think of a pathological example against that is if you had an entirely classical circuit with dephasing noise. Well, this wouldn't happen because the dephasing noise wouldn't do anything. So
Thanks.
So just to summarize the algorithm, you sample poly projections, you propagate them to the beginning where they replace some input qubits with maximum mixed states, you replace every gate acting on two maximum mixed states with an identity gate, and finally you simulate the resulting subcircuits independently. So as Antonio pointed out, I haven't made any approximations yet. And actually, this algorithm is an exact sampling algorithm. And the interesting part is the runtime depends on how big these components are. So it has a random runtime, and you can actually bound this and show its polynomial and expectation value. So this is called a Las Vegas algorithm in computer science. And the more common thing that you've seen before is an approximate sampling algorithm with polynomial runtime, or called the Monte Carlo algorithm. And the Las Vegas algorithm actually implies the Monte Carlo algorithm. So I can just throw out the events where I have too big, where my system doesn't split into subcomponents. And if I throw out these events, I get a small approximation error and fixed polynomial runtime. So every time you show a Las Vegas algorithm exists, you can actually convert it into a Monte Carlo algorithm. And this is sort of a strong, that also means that the existence of this exact sampler with random runtime is a stronger statement. And yeah, I'm not sure fully how it relates to the complexity theory yet, because I know there's actually interesting differences between exact sampling and approximate sampling hardness. But this is basically one interesting thing about this algorithm is that it's one of the first exact sampling algorithms out there.
Can I ask you something, Joel?
Yeah.
It's really cool to know this kind of things, but I'm curious, will we know for a given sample of an IQP circuit whether it will have polynomial runtime or not? Will I know whether I should discard it when I stand with a concrete circuit I want to simulate?
Like what you're saying, will there be will it pass the depth phase transitions? What you're asking?
No, more like you're saying that the math goes on, that in expectation things will go out, and then you can just throw away the things that will not on expectation people know.
Yeah. So this because you've sampled a noise and then you split it into smaller subcomponents. Now you can just check the size of these subcomponents. If the subcomponent is greater than log n, then this is an event that you throw out.
That makes sense. Thank you.
Yep. So how much time do I have? Maybe 10 minutes. Okay. I'll try to quickly give you some intuition for the analysis, because I know Antonio might like this when we've talked about stuff like this. So I'll try to give you this. Basically, once you propagate the noise to the beginning, how do you rigorously prove that many of these qubits become maximally mixed? And this is sort of an opportunity for us to kind of think about, right now this algorithm is a little bit more different from existing techniques, but having to solve this problem lets us actually relate it to a lot of existing techniques. And we think that this might be useful more generally. So our idea is going to be to write the input state as a sum of poly operators. Then the way you can prove that many qubits become maximally mixed is prove that noise destroys most of the input poly operators. And therefore the noisy state must be very mixed. and actually more formally, a large portion of it includes maxi mixed qubits. So this actually lets us connect it to this polypath analysis, which is a large body like of existing work. Random quantum circuit simulation uses this toolkit. Very roughly, the idea behind the polypath analysis toolkit is that you can decompose your circuit evolution into a sum of exponentially many polypaths. And when you have this model with depolarizing noise after every layer, paths with high weight terms, fewer identities, decay more due to noise. So maybe your path started off with a few X's and Y's, and throughout the circuit, it can go up and down in weight. But when you look at the total weight, this kind of characterizes how many depolarizing channels it experiences and how much it will decay. The idea is that the depolarizing channel doesn't decay the identity, but it decays the X, the Y, and the Z polar terms. So what the main idea behind many of these existing polypath analysis works is that you prove that the decay overwhelms the number of polypaths, and this will tell you that the low weight polypaths are a good approximation of the full circuit.
But this is like basically, I mean, this is like the idea that can be traced back to, I don't know.
Yes, yeah.
The Gaussian boson sampling simulation techniques that also Dominic and myself like reviewed in great detail in our review, and then it was kind of reinvented by Dorit and others in the
that paper.
Pauli in the qubit simulation thing. That's kind of the thing. Like go to the Heisenberg picture, count paths, and then you see that you have many, but most of them don't matter.
Exactly. Yeah. So one of the way the existing work kind of goes is the decay of the polypath it scales with the weight. So you can think of it as e power minus gamma w. Then the number of the polypaths with weight w is this exponential thing. So this is just, I've copied this from like, as I said, Aaron Aho's paper. And there's a lot of work that actually uses the same thing. I didn't cite them all. Maybe I'll go in later and add a bunch of citations, but a lot of classical simulation work actually uses this same sort of counting argument. So the idea is that when you multiply these, the contribution of polypaths is just the product. And if you notice, you have this exponentially growing term, which is the number, and an exponentially decaying term, but there's a gamma in front of it. So this isn't enough. The decay doesn't overwhelm the number, just right off the bat. So you have to add these other assumptions like anti-concentration, as I mentioned earlier, or sometimes if you can get away with just, if you just want a single observable instead of an output distribution. But there's a lot of different things people do to try to solve this problem, which is that the decay and the number the decay doesn't completely overwhelm the number. So you need an extra tool like anti-concentration. And basically what we've done here is our improvement is that for Clifford circuits, you can actually show that this number is not O of e to the O of W, it's e of O to the W by D. So this is sort of getting at the idea that the larger depth you have, you can actually bound how many polypaths you have. You can actually, the larger depth is actually easier to simulate than the shorter depth, right? The depth is introducing a decay in a sense. So now when you do the math, you have this variable D term that lets you take out some portion of the number of polypaths. And skipping some steps, this lets you get simulatability at omega log n for worst case Clifford circuits or IQP circuits. So I know this might have been very like high level because I'm trying to avoid getting into the details, but maybe the main takeaway is that like we're able to get some improvement by restricting to Clifford circuits, and this improvement is in the counting argument in a sense. So now just to like maybe pause for a second on this counting argument, it actually doesn't have to do with the Cliffordness. I'm going to try to maybe give you a high level intuition for why it works. The main idea is that Pauli operators which start off with high weight must stay high weight throughout the circuit. So existing bounds from like Aaron Vidal and a bunch of other work they kind of have a loose bound on how much weight is in each polypath. But the intuition is that they may actually stay relatively the same weight. So, and if you stay relatively the same weight, then after D layers, you basically every layer is introducing more and more weight, and you can actually bound that. So in Clifford circuits, we can make this rigorous, but I actually think this idea that like high weight polys map to high weight polys and stay high weight throughout your circuit, and therefore you get like a D term in your exponent because of how many layers you have. I think this is a sort of a general idea. But yeah, that was the analysis. Do you have any questions? It's okay if you didn't fully go through that. I was a little vague here, so but yeah, any questions?
Like this Pauli path is used only for the log n depth threshold or also for the constant depth?
So it's used for both. So so if it's used for the log n depth threshold, and then I need it in order to prove that some portion, which is like log n size, for example, becomes maximally mixed with high probability. So that's another thing I'm not saying here, I guess, but this same counting argument now lets me say that, remember, so this earlier point I was making here, that I want to show that noise destroys most input poly operators. This whole argument actually, in effect, it lets me say that different portions of the circuit become maximally mixed. Because I count the polypaths and I look at the decay, and then I show that the decay has overwhelmed the number of them. So now the only thing remaining must be the maximally mixed state in the small area.
Okay, thank you. So both proofs of the two main theorems leverage this new counting argument for Clifford circuits. Okay.
Exactly. Yes. Yeah.
Thank you.
Yeah. So now I'm going to talk a little bit about future work. I got like 2 minutes maybe. I'll try to make this quick. So yeah, as someone asked earlier, is it hard to approximately sample from a depth below this critical depth threshold? I actually think it might be true. It would be hard to prove, but if you could prove it, it would be a circuit that provides scalable quantum advantage for sampling and fits in the NISC era. This is like a good open problem to think about if you're interested. And this basically maybe lets you, our work tells you what you can't do, but I do think below this critical depth threshold, there might be hardness. Second thing this lets you do is it lets you put some limitations on near-term fault tolerance ideas. So one thing you can think of doing is encoding a noisy physical circuit. Constructing a noisy physical circuit that encodes a logical quantum circuit, where the logical output distribution can be recovered through classical post-processing alone. So this is sort of an idea that's important in the near term because maybe you don't do intermediate measurements. And this is sort of the definition of NISC in a sense. And our results showed that if you want to go past a certain depth, you can't do this within the IPP or the Clifford magic framework. You need to be able to do other gates. So there's some caveats to the numerics. The expected runtime does not depend on the noise strength. It's actually practically feasible. This is doesn't have this annoying gamma term, the exponent to the gamma or some reverse gamma or something like that. But the bad news is that the depth is actually very large for practical noise levels. So this is just a graph from an earlier work with IQP circuits. If you have a 1% depolarizing error, the depth this critical depth happens at around 300, which is much larger than what we have with current computers. So like it's interesting in the sense that whether you have 1,000 qubits or 1,000,000 qubits, it's still, when you go to 300 after this, you're classically simulatable. But 300 is still a while away, and if you want to make this a practical algorithm.
Sorry, I cannot pass this, but this is me lacking maybe, well, I don't know why that is. But you say it's practically feasible, and then the critical depth is large for practical noise levels. I mean, it will depend on the critical depth will depend on the noise level, right?
Yes, yeah.
Then also the expected runtime will depend on the noise level because, I mean, you have to go to the critical length or not.
So once you pass the critical depth, it doesn't depend on the noise level anymore.
Ah, okay, I see. But that this I understand. And then it's practically feasible. You mean just it's in principle possible, but this may be still very hard to do in practice.
If you wouldn't find a circuit that is that, like, you probably wouldn't run a circuit that deep in the near term is what I'm saying.
Okay, good.
So yeah, the summary is that noisy CM star and IQP circuits are classically simulatable when their depth exceeds a constant threshold. And the main takeaway is that if you want to do a fault-tolerant implementation of CM star or IQP circuits, you should leave this framework somehow by measuring with feed-forward, supplying fresh qubits, or universal gate sets. This is maybe sort of, for you guys might already see this as intuitive, but I think this is sort of maybe an important message that this is giving, which is that, you know, the noise defeats you, you have to do measurement with feed-forward or supply fresh qubits to get around it. And yeah, so that's the main content of my talk. Do you have any questions?
We had lots of them.
Yeah, maybe just this one. I made lots of questions already, but what do you have an intuition for any types of noise? I mean, like other types of noise, like different from Pauli channel, like non-neutral. I mean,
it's tough because I'm thinking about worst case circuits here, right? And one of the problems is that I think you can design a worst case circuit with amplitude damping channels, where you just let some qubit idle for a bit under an amplitude damping channel, and it effectively introduces a fresh qubit. And now there may be a way to intelligently design a circuit that uses that fresh qubit and does fault tolerance for an indefinite amount of time. So there are some papers that do this for amplitude damping noise, not within the Clifford Magic or IQP framework.
Yeah. My question was for this restricted gate set, because there are these refrigerator construction that show that you don't need the measurement and the supply of fresh qubits.
Yeah.
But they don't have restriction on the gate set. I was interested if you had the intuition if restricted to this gate set. But
so yeah, I think my intuition tells me that I think Clifford Magic may be hard if you have amplitude damping noise. IQP circuits may be easy. That's just sort of my guess, even with amplitude damping noise.
Because at the end, I guess for this refrigerator construction, we need just to be able to implement the swap gates or something. I don't know. So Clifford would be fine, but I don't know.
Yeah, I think Clifford would be fine for that refrigerator construction. But yeah, IQP circuits, it's not clear. Also, the intuition is the IQP circuit, the noise is taking you to a something with less coherence, right? Like you start with the plus state, and depolarizing noise takes you to a maximum mixed state. Damping noise would take you to the zero state, which also is bad for generating entanglement in the circuit. You know, a diagonal gate acting on a zero state can't do anything.
But the swap gate is in the IQP class diagonal gates that you're considering or not?
In the newer result, we think of IQP gates with CNOTs, and that includes a swap gate.
Okay. Yes.
Yeah. So I mean, like one motivation of all this is to find new ways forward and to get like actionable advice of what to do next, right? Because that's a building block towards there's fault-tolerant quantum computer, right? I mean, we have like some preliminary results that your first part is true, that some measurement will help in reducing the requirements to go beyond classical simulatability. That seems to be true. But then is it, as a general question, I mean, there seems to be increasing evidence that depth is worse than width. Is that a take-home message, that it's easier to make large circuits than to make deep circuits? In a way, because you get easier classical simulation results for shallow circuits than for.
So you're saying it like I think that's a good way to phrase it. That the deeper you go, you might be attackable by a classical simulation algorithm, but if you increase the width and keep it shallow, and somehow are still able to show hardness, this would be right.
I see.
You also show that it's hard to sample for under a certain depth or not?
So that's not in this work. In the other work with James and Yikai, for IQP circuits, we showed there's an exact simulation hardness below this threshold.
And for this, it's technically challenging to show the same, or what?
I think it wouldn't be too technically challenging. I guess I think it's definitely possible. I think the problem was it's only showing hardness of exact simulation, and I think it's more interesting to show hardness of approximate simulation. And I don't know how to do that. That would be really the thing that I'd be after.
Well, in the previous work, was hardness of approximate or always exact?
It's exact. Yeah.
Okay.
Yeah. So it's not very hard to construct an exactly hard to simulate circuit, because showing of hardness of exact simulation, one of the tools you can use is to post-select. And if you show something's hard with post-selection, then it might be hard with exact simulation. And then once you can post-select on like noiseless events, and it makes the proof technique a lot easier. So yeah, I think the more interesting thing is if you can show hardness of approximate sampling for these circuits, and that I think there's no results.
Sorry, speaking of noise, do we have any results that talk about classical simulation or advantage in sampling when you have noise that is like temporally correlated?
Oh, good question. I don't have any results. So this means that like it's not Markovian noise?
Exactly, yeah, that's right.
Yeah. I haven't looked into it. It's an interesting question.
It's difficult. I mean, it depends on how you formulate the question, because I mean, there's some temporal noise that's very difficult to tackle. Like, I mean, there's a Martian landing and providing a new quantum computer and then providing you new data. That's one very temporally correlated thing. Or you get a meteor falling down and just killing the whole device. I mean, these are all temporally correlated errors, and it's hard to exclude them from your prescription, right? It's also easy to even formulate the question in a way that becomes a mathematically answerable question.
I think you can restrict the class of noises in the same way that you do to regular channels here, right? Like,
yeah, you're the right person to ask. That's right.
Like here, you have to simplify the noise to be unitary, like it has to have a depolarizing component. Like,
Yeah, that's right. And then think of Combs or like Markovian noise.
exactly. You can apply all the same sorts of
Yeah, good.
It's like correlated as a like that.
I agree.
And actually, probably this algorithm would work in that sense anyway.
I mean, maybe coarse grain, and then it becomes like a coarse grained big thing with IID noise, and then.
Yeah, we should do that.
No, that's right. No, actually, that's a mental note. Yeah, the experts, might be nice because it's maybe a relatively low-hanging fruit, although the devil is in the detail to then decouple and make sure that the tails don't matter. But
yeah, I think the tails is a big problem.
So I think that'd be really interesting, because also I think there's not a lot of work that deals with non-Markovian noise. Like
Yeah, and I think the techniques will also fail because these Arnov et al. Techniques that in the Pauli path sampling literature, they kind of make heavy use of I think these old results from Harrow and others that have random quantum circuits with some sort of noise in between. But then I think even on that front, there's little work that has random quantum circuits with non-Markovian noise, and then sort of making statements about those. So I think maybe just the lack of results on the fundamental level is the reason that people have not looked at this question.
A draft, I think, about this case.
yeah, that's right. We should come back to this.
Yeah, and a second question, sorry, I don't want to hoard everyone's time, but then I wanted to square this result with the original Bremner-Shepard result that said that if you could sample from I guess an IQP circuit, then the polynomial hierarchy will collapse to the third level.
Yeah.
Is it is a way out of this apparent contradiction that
so
this I'm not sure how to square this with that result actually.
Yeah, so that result only deals with the noiseless circuit.
Right, sorry. Yes, that's right.
So yeah, it's true that the noiseless circuit would collapse the polynomial hierarchy. The idea is that the noisy one changes it, not like non-trivially.
I see. And it's still not, is it known that that in the noiseless case, sampling on average case is still hard?
Yes. The noiseless case, there are even constant depth IQP circuits which are hard to approximately sample.
In the average case?
In the average case, yes, yeah.
Oh, okay, cool.
Yeah.